Hi everyone, my name is Brent Harrison, and I'm an assistant professor of computer science at the University of Kentucky. Today, I'd like to talk to you about some of the work that me and my colleagues have done on generating explainable interventions for analyst workflow. This work was done for the Laboratory of Analytic Sciences as a part of their human-machine collaboration team. This project is about generating interventions that are meant to help analysts through their workflow. In order to do that, we first need to understand exactly what their workflow happens to look like. When an analyst is presented with a novel dataset to explore, they often approach this task in a very principled way. However, it can be difficult for them to convey exactly what that process happens to be. Thus, the first thing that we want to do is construct a computational model of this workflow. Once we have this model, we can use it to develop interventions by tracking an analyst's progress through this model, and then recommending actions for them to take based on what the model says is likely to happen next. To model workflow, we wanted to construct what we've been calling a workflow graph. Now, nodes in this graph are going to represent analysis actions, which could be anything from reading or searching for specific documents to using a visualization tool to get a better sense for the dataset in question. An example of an analysis action might be reading a document about software server shutdown. Edges between nodes represent precedence relationships in which one action needs to occur before another one can. In this example, edges in the graph indicate that reading the document roadnav.exe uploaded to software server needs to occur before reading about hardware upgrades. To build this graph, we drew inspiration from past research on constructing graphs from action sequences that were gathered from many people. In this work, the first step to constructing a graph is to determine what actions go in the graph. So these would become the nodes in their graph. So this is done by identifying common actions that occur across many of the gathered sequences. Edges are then added to this graph one by examining how often certain actions are performed before others in the gathered sequences. We plan to adapt this approach to our project by making use of what we call analysis trajectories. Analysis trajectories are just sequences of logs that detail how analysts interact with a specific data set. The issue with this approach is that there doesn't exist a high-quality dataset for this task. While there did exist many datasets on documenting how analysts interacted with data, we found that they were missing several pieces of information that we needed for our project. One of the critical pieces of information that was missing was information on intent. Information that could be used to understand why specific analyses were being performed, why certain documents were being read. We found this to be especially important because this information could be used to determine how analysts form, confirm, and reject hypotheses.
Since we couldn't find the data we needed, we decided to collect our own. We developed a serious game to be played by intelligence analysts that could be easily deployed via a web browser. The game takes place at a fictional startup company that has experienced an insider attack, meaning one of its employees conspired with an outside source to steal the company's proprietary software. You play as an investigator, searching through a large collection of documents recovered from that company's computers. These documents include emails, calendar entries, network logs, and other sources of information like news articles and web pages. The game is designed to simulate the tools used by analysts and to collect detailed logs about how they carry out their analytic process. Analysts can search the database of documents using a number of different parameters. Here, the player is searching for any emails involving Michelle. Every time they perform a search, we ask them to provide an explanation for why they're performing this particular search and what they hope to find by doing it. The the results of a search can be displayed as a table of documents, as an interactive map, or even as an interactive timeline that helps analysts discover the relationships between different kinds of documents. As analysts investigate, they can find new documents to add to their database, either through a fictional web search engine that lets them learn more about a specific topic, or by recovering files that were deleted from the company's computers. When a search leads to something important, they can save those search parameters or individual documents for later. Anytime they save something, we ask them to explain why they think it is important. Players can then use the searches and documents they saved to build up a case for or against each employee in the company using a drag-and-drop interface. The goal of the game is to find enough evidence to conclude who committed the insider attack. After each participant is finished, we conduct a brief survey to collect their age, education level, and experience as an analyst.
The data is generated when the user takes an action in the game. Many kinds of actions are logged, including but not limited to the user making a search, viewing a document, and even switching between the tools and data views. We were able to collect data from over 20 users and are still collecting more. This rich data set of every action taken during the analyst process, annotated with their intentions, is one of the major contributions of this project. With this data, we are developing two different methods to combine it and extract a usable workflow graph. Our first approach attempts to find which actions contribute to which goals in the individual user. Then we'll group based on these goals with other users to create a workflow graph, while the second combines the actions from multiple users into a workflow graph and will group by goals afterwards. This graph is based on an individual user and compresses their actions into a nonlinear directed graph. One is made for each valid user. Working from the top down, it follows the user as they attempt to find the culprit in our scenario. The graph contains two main types of nodes: search nodes, marked in diamonds, and examine document nodes, marked in ellipses. There's also a start node before their first action, and an end node that shows who they accused at the bottom of their last action. When the user saves a document or search as potential evidence, it is shown separately and marked in blue. Potential evidence that was later used as evidence against who they accused is further marked in red. Splits in the graph are when the user has revisited a search or document that they have saved. From this, we hope to extract higher level actions and group based on these actions with graphs from other users.
We built an intelligent workflow graph using 20 people's data. This directed graph represents the general workflow of all users. The nodes of the graph are the common events that occur across most users. An edge from a node A to another node B in the graph means that event A happened before event B in most user transcripts we examined. Let's look at an example graph. From here, we can see that users generally explore interview data first. After they read this interview documentation, they begin to explore information related to the software that was stolen. And then they look at other documents that could be considered suspicious, such as read sick day, read timesheets. Eventually, they find information related to a competing company. And this ultimately leads to them make their final accusations.
This research was performed at the University of Kentucky by Professor Brent Harrison of the CORGI lab and research assistants Cheng-Shi Li and Anton Vinogradov. also by Professor Stephen Ware of the Narrative Intelligence Lab. We'd like to thank all the members of the Human-Machine Collaboration Team at the Laboratory for Analytic Sciences, and especially Yasha Swisher for his help in delivering our serious game for data collection to an analyst population.